Hey, this is Andrew McLaren. Today we're going to talk about acids and bases and their conjugates. There's a really common misconception that I want to address in this video. Uh, Basically, a lot of people think if you've got like a strong acid that it's going to conjugate to a weak base, and therefore a weak base will conjugate to like a strong acid. But there's a lot of chemicals out there where you have like a weak acid where its conjugate is actually a weak base. And so it's really, really important to recognize that not all weak bases pair with like strong acids. And so to help understand how like the strength of the acid in the base relates to its conjugate strength, we're going to be looking at just the main idea and helping you understand like what it really means to be an acid and a base in this context and the strength in this context. And then we're going to look at some weak acids and bases and strong bases and really think about what those things are and look at some math. So I've got like a number of things that we're going to look at to help you understand what's going on with these ions and helping you compare these different situations. So yeah, well, you should be able to relate not just the strength of these things, but like some numbers that correlate to their strengths, because that's how we talk about the strengths of these acids and bases. And then you should be able to like compare things and say what's a stronger acid or a stronger base, because you are going to need this in organic chemistry. If you're like a biology or a chemistry major, this is going to be central to college classes. So you got to understand the basics of acid and base strength. Okay. So when we're talking about acids and bases in general, when we're talking about the conjugate, it's the thing on the other side of the reaction. So you've got some reactant and some product, and so you can have an acid, and then it's going to have its conjugate, which would be the conjugate base. And you can write this where you have water reacting with the acid, and it produces this hydrogen ion. Which is oftentimes written as just H plus, though it really is H3O plus. We can also consider when we're looking at a base and it's reacting with water, it's going to be like accepting protons, and that would leave like the hydroxide ion there. If you get rid of one of these H pluses, you're left with OH minus, right? So that's the main idea with acids and bases. And I've given you a couple examples of an acid and its conjugate base, and this acid and this conjugate base. Now, actually, both of these are weak acids and weak bases. And a lot of the time that is the case. Most of the time when you're working with a weak base, its conjugate is a weak acid. Unless we're talking about like, it gets a little bit weird when we're talking about the super strong acids and bases, but this is the main idea. So if we say like most of these things, most chemicals for most weak acids, they're going to have a weak conjugate base. If you have a strong acid, this is kind of like a base, but it's so weak of a base that it's kind of a stable ion. And so it's not very good at being a base, but it's still technically a base. But it's like if you had like 100 million of these things, maybe one would not dissolve. Like all of it's going to dissolve and maybe one would not dissolve, but effectively zero is going to stay here. So we say 100% goes. Same thing with the strong base. These things are terrible acids. They are technically still weak acids, though I like to think of them as stable ions. And so if we're really thinking about how all these words are related, this graph right here, or not graph, it's kind of like a Venn diagram, helps you kind of understand how these words are all related. Oftentimes you have weak acids and weak bases that are paired with each other. But then you have these things that are really unstable, like hydrogen, we've got like our sodium hydroxide and our hydrochloric acid. And you know that like chlorine, it wants to be a -1 charge. It's very stable like that. If you know your periodic table and those trends, then you know that this is a very stable compound. This is super unstable. And so like almost all of it's going to turn into that. And same thing with like sodium hydroxide. If you have sodium hydroxide, it's going to want to ionize into the sodium plus and the hydroxide minus. And this is very stable. We know that from our periodic trends. This is pretty unstable. And so what we basically have is like for most things, these are both fairly stable. One might be slightly more stable than the other one. Like if you've got a slightly stronger acid than its conjugate base, you can talk about it being a slightly stronger or slightly weaker acid. But these both are fairly stable. One might be slightly more stable or less stable, which would then cause equilibrium to kind of be more common with you'd have more of the stable ion with those K equilibriums, basically. So that's like the main idea between all these things. And then also you can relate the strength of these acids and bases. If you've got like a stronger acid, its conjugate base will be weaker. If you've got a weaker acid, its conjugate base will be stronger, right? And so when we're talking about an acid's strength or a base's strength, we're oftentimes either talking about Ka or pKa. And it's important to note that when the acid's strength is going up, its Ka is going up. You know, it's favoring the products. It's making more of the products in a sense when we have a high Ka. So if we have like a Ka that's a big value, it's saying like, okay, you're going to be a very good acid. You're going to donate a lot of protons. So it's going to have a bigger Ka value. And then its conjugate base is actually weaker. And these things are related through Kw. So this is one of your formulas, Ka times Kb equals Kw. So the stronger an acid, the weaker its conjugate base is. They're probably still both weak acids and bases. 99% of the time that we're talking about this, we're talking about a weak acid and base. So when you're seeing Ka and Kb, that's indicating that you're working with weak acid base pairs, where one is more strong and one's slightly more weak, but they would both be classified as weak acids and bases. So this is just how we get the pKa. It's a negative log. So remember when you do a negative log, like 1 times 10 up to the negative 14, when you negative log that, you get 14. And so it kind of like flips things upside down. And so when you have a big K value, that causes a small pKa value. So if you had like, let's say your Ka was 1 times 10 up to the negative 4, and then your Kb was 1 times 10 up to the negative 10, then your pKa is going to be 4 and 10, right? And you can see if you were to actually make this number get bigger, that ends up making like 10 up to negative 3 is actually a bigger number than 10 up to negative 4. And so a bigger number ends up getting smaller values on your pKa scale. And so you can talk about the relative strength of the acids and bases by looking at their Ka values or their pKa values. They're just either looking at in terms of how big and small it is relative to 1, or looking at those exponent values. So I also have this table that I made, and I made it from like a couple different resources. I've kind of like thrown them together, but I have a couple different acids and bases and their Ka values, pKa values, pKb, and Kb values, also talking about the relative strength of the acid and the base. And this to me is super, super helpful for understanding how these things are related, in addition to this little Venn diagram. So if you look here, these are strong acids like HCl, that's a strong acid. When it dissociates, it's going to form mostly the chlorine ion, right? And we've got like I think this is generic HA and A minus. I think I just gave you the generic ones right here. So this is actually not included. That should be more like this. And then you've got your hydroiodine. I'm not sure how you pronounce that one, but then you got the iodine ion. And so these things, they are technically still bases, but they're very stable ions. And then this is more of like what you're used to kind of seeing with the Ka values that you're used to kind of seeing. I will talk about these Ka and pKa values in a little bit for the strong acid, but they're kind of the exception to the rule, because it's pretty clear when you look at your weak acid base pairs, that like, okay, this guy right here, pretty strong acid. It's got a low pKa value, pretty big pKb value, right? So it's a strong acid. It's got like this low pKa. And then you can look at like this guy right here. This is a weaker acid. This is a pretty weak acid. But then this guy is a fairly strong base. So it's, although this is a weaker acid, this is a stronger base. Now I wouldn't classify this as a strong base because it's not going to go like 100% in the basic direction, but it's a fairly strong base. These pick up protons quite a lot. And you can kind of see that here where it's like, compared to water, this is going to be picking up protons. Like it's going to make it more basic than water normally would be, because water normally has a pH value of 7. You can think of that as like a pKa value of 7. And so like any of these things down here, when you mix them, if you had like the same amount of the acid and the base, this is going to cause a basic solution, essentially, when you mix that with water. So you can kind of see that these two numbers, they do add up to 14. That's also one of our rules, is that the pKa and pKb should add up to 14 always. And so you can kind of see how the pKa and pKb, how they always add up to 14. And when one of these goes up, the other one goes down. You can also relate this through the Ka and Kb. If you multiply them, that's the same thing as like adding the exponents. So this is the Ka times the Kb, and if you multiply those together, like if you get your calculator and do that calculation, it's a little bit messy, but we can do that. We can do the 5.8 times 10 up to, what is that, the negative 10 power, right? And then we're multiplying that by the 1.7 times 10 up to the negative 5th power. And then I think I did something weird here. Yeah, there's something weird in my calculations here, because this should be coming out as 10 up to the negative. So let me see what I'm doing wrong. It's just that I hadn't entered the the button. I hadn't entered the enter button. So anyways, this is actually, if you were to go through this like 1, 2, 3, 4, 5, 6, it's going to be as if this was actually 1, right? And then that would be 1 times 10 up to negative 14. It is slightly off because I rounded some numbers, so it's ever so slightly off. But in the grand scheme, that was basically 1 times 10 up to the negative 14. And so you can kind of see how the pKa and pKb, they do multiply to give you Kw, as long as you're working with the right Ka and Kb pairs. And then their pKa's should add up to 14. And you can see that if you know your exponent rules, you know that this is like 10 up to the negative 9.3 is the same as 5.8 times 10 up to negative 10. You can think of this, if you were to make this like a little bit smaller, this needs to be made a little bit bigger, the number that's in the exponent and this coefficient. You can think about bringing that coefficient down to 1 in a sense, and then this needs to go up to negative 9.3. So that's kind of like, okay, this is that number, right? This is that. To help with the seeing that, I suppose we could make that kind of like that there. So you can do that for any of these pKa's and pKb's, and I would recommend you do that. Now the weird thing, now this is pretty weird, when we're talking about a strong acid and a strong base, the exact cutoff point isn't clearly defined. It's not like widely accepted, but in general, you have a strong acid when it's the equilibrium's so out of balance, it's pretty much all 100% either product or reactant. And so you can imagine this going to being 100% the products. And essentially what ends up happening is that like this is, the pKa is going down and then it gets to a point where it gets so low that it actually starts to become negative. And that's basically saying that you have a huge Ka value, because it's like the negative log is now a negative number, which means a positive exponent. So when you have these strong acids, they actually don't have Ka values with negative exponents. They start to get these positive exponents, essentially because they're all going forward. If you're thinking about like K being the balance of the products over reactants, remember K is equal to products over reactants. If you've got a very large K, that means it's like all products and no reactants. So the acid has basically fully dissociated and there's like none left and it's all products. So you can think about that as like being like the strong acid point where the pKa keeps on getting low, and in general people say a pKa of like 1 or lower is going to be a strong acid. Or if you had like the flip side, the bases, if the pKb keeps on getting smaller, that means it's a stronger base, and then it flips into being considered a strong base at around a pKb of 1. And if you can get to becoming a negative number, then that's a very strong base. And you can think about the same thing here. This is a pKb favoring the products. And so if we're talking about the Kb, we're talking about a base, like a strong base. And so it's almost all product, almost no reactant. And so that is going to result with a large K value when we're talking about these things. And it's kind of weird because this is a very small number by default with water. And same with these. So the fact that the K value is large with hydroxide ions and hydrogen ions is that much more impressive. It means that there's that much more stability coming from this other thing. And so it's super favorable to be those products in a sense, right? And so if you were to think about labeling a couple of these things, it's good to be able to compare the stronger of the two acids. So although these are both considered both weak acids, for these two, you can say that I think we're looking at the NHNO2 and HS. So NO2, it looks like that was a stronger acid than this other one because it's got a lower pKa. It's got like a bigger Ka value, so it's got more favorability to dissociate. Because remember, when you've got a smaller negative exponent, that's a bigger Ka value. This is why I like to do the videos, because you can go back and re-listen to any particular part that I said something. And then if you think I said something wrong, put a comment, timestamp, let me know, and we can clarify that, right? So it looks like, I think this was our stronger acid, right? Yeah, compared to that. So although they're weak, they're both weak acids, this one is slightly stronger. It's like if, you look at two people who both can't lift up very much weight, one person's going to be a little bit stronger than the other. They might both be weak, but one person's stronger, right? And then the stronger base, the N3 minus or NH3. So if we were looking at the NH3, N3 minus, I think this one is the stronger base. Yeah, it's the stronger base because you can think about it as favoring the bases. Like this is a pretty big pKb value. So it's going to be favoring producing more hydroxide ions than water would like to normally have in general. So you can talk about that and say that the NH3 would be that stronger base. So that's the main idea. And then we'll go over some more like calculations in the next section to help you kind of understand how these things relate to their Ka values and whatnot, and compare them, okay? So the main idea when we're talking about a weak acid and a weak base, when they're paired up together, effectively you're gonna have a little bit of both in the solution. Like in the final situation, you'll have a little bit of both. You might start off with all of just one thing, like maybe you've dissolved a salt like there's some sort of salt with ammonia and maybe chlorine, like NaH4Cl is a really common salt that you see. Um, Maybe that's dry and that's being dissolved in water. And so you might start off with all of your reactant, and then some product is going to form. And so this is what we would consider a weak acid. And then you could actually look at the opposite situation. If I changed these to blue, then I would need to change these also to blue and these to green. Like this is a weak base. If it started off being all this, then some of it will change to the acid, but not all of it. They'll strike a balance between the two. That's the main idea. The math that goes behind it is a little bit complicated because we're dealing with exponents, which just makes these numbers that much harder for most people. But this is the main idea. A weak acid and a weak base, they're not going to completely dissociate. And so their conjugate will probably not completely dissociate as well. That's what I consider to be a weak acid or a weak base. And that's kind of why I have a hard time considering these ions to be like weak bases, or like these ions to be like weak acids, is because they don't really strike a balance between themselves and their conjugates. It's just all of them, you know. So at the like high school level, you'll typically see people tell you that these are not like acids. They'll just tell you that it's just not an acid. But at the college level, they'll probably be like, yeah, it's an acid, but it's just incredibly, incredibly weak. And it makes you don't see K values for acids really, because or acids and bases that are strong acids and bases, because the K values, they're just kind of weird and they're inconsistent. These guys, you always get consistent Ka and Kb values. And so I've just rewritten what I had earlier, where if you've got like a stronger acid, it's going to have a partner that's a weaker base. And so you can talk about the weak acids and bases strengths relative to each other. And you can rank things with like pKa's and pKb's and compare them and say how much would they probably give hydrogen off or accept it compared to other chemicals. Also keep in mind that pKa and pKb for weak acids and bases, these are normally small values. They are dissociating, but they're weak, so it's not very much. And so it's typically in the range of like 1 to 10 up to the negative 1 or 1 to 10 up to the negative 14 for those K values. And you can think about that as like effectively being the if you had like a pKa value of 1 and 13, that would be the same thing as 1 times 10 up to the negative 1 times 1 times 10 up to the negative 13 for our Ka and Kb values. And so anything between these two numbers, you're going to have a Ka or a Kb value that kind of works for the other conjugate in a way that would allow it to also be a weak acid or weak base. So you could also have like 2, 12, or like, 6 and 8. And so you can talk about like these values in what you're typically expected to see for the pKa's and pKb's for most chemicals. And then the Ka's should be like 1 times 10 up to the negative 6 or 1 times 10 up to the negative 8. And those are typically what you're going to see for those. So if we have this reaction where we've got the ammonia and ammonium, I think this is ammonium and this is ammonia, right? You can have its pKa value. And let's say that you have 1 molar of the NH4 plus. This is going to want to go to in its equilibrium constant. It is a weak acid, and so it's going to give off some protons, but not very much. So this will dissociate, but it's not going to be very much. Like these, we expect to be small. We know that that will be small because the um, the K value that we're working with is small. Doesn't matter if it's Ka, Kb, or just a generic K. If it's small, that's basically saying that the product and the reactants balance, if you look at it, there's not very much product. There's mostly reactants um, in this dissociation, right? And so it's going to be, if we were to write that as a Ka value, this is that reaction, its K value written out, the products over the reactant. And this is so small because that small K value that we can just ignore it and get rid of X, because it will be small compared to the total amount of product. It wouldn't really change the amount of product that we're looking at. And so you can do a little estimation here. This is an estimated X value, so probably not exact or perfect, but it's close. And so we can say that that's the concentration of the hydrogen ions right now. So if we have our picture and we're imagining this is 1 molar that's been dissolved, and you've got our green and our blues, this is basically saying like, okay, this is how much of the product you made. So you've got like 2.4 times 10 up to the -5 for those blues. So this is that. I think we had that as the blue and the black in our diagram, right? And so there's that certain amount of product when we're considering those ions. But if you were to then consider the basic reaction, now we're dealing with a slightly different ion. This is hydroxide. So it's the same situation. We still have the same amount of these two chemicals. I'm just wondering how much hydroxide we have. And you can actually plug these in. We can figure out the Kb because we know the Ka. We know what the Kb is because Ka times Kb equals Kw. Or let's just say that it's been provided as well. Basically, if you know Ka, you know Kb as well. And if you know Ka, you know pKa. If you know one of them, you should be able to figure out all three of the other three using those relationships. And then we can think about this as a little bit of an algebra problem. And if we solve for X, this is how much hydroxide ions we have. So in this solution, we currently have that much hydrogen and that much hydroxide. And you can see if you were to multiply the hydroxide, the concentration of the H times the concentration of the OH minus, this is actually also still equal to the 1 times 10 up to the -14, that Kw. This is the definition of Kw. So in this situation, you can see like, oh yeah, this has produced, when this dissolved, it produced more hydroxide ions than water normally has in it. So you can kind of see in this situation like, oh yeah, water normally has 1 times 10 up to the -7 of these ions. I've got 2 magnitudes bigger than that. So this is a slightly acidic solution. And then that also means that if you look at the pOH value, the pOH right here, this is showing that it's a slight, it's not very basic. It's slightly acidic. So if you've got a low pOH value, then you've got high pH value and vice versa. And so you can look at those concentrations as well and see how they compare. So that's kind of what's going on here. The interesting thing to note is if you did the same dissolving, but you had 1 molar of NH3 and it dissolves, it's going to do very similar to what the NH4 plus did. It's going to start off as all of its reactant. That, like, if we were to consider the NH3 and it reacting with water to produce the NH4 plus and the hydroxide ions, You could look at that reaction and say that you have like 1 molar of this, and some of it's going to dissolve. So we are going to get more hydroxide ions than you would normally see, but it's not going to be like completely dissolved. And because there's going to be more hydroxide ions than what you would normally see, there'll be less hydrogen ions. So if we are working with the conjugate base, we're kind of doing the reverse in terms of what's going to be more or less produced. Like if you were working with the conjugate base and letting it dissolve, it will make the solution slightly basic. If you're working with the conjugate acid, you let that dissolve, it'll make the solution slightly acidic. It depends on those initial conditions. If the solution is going to be acidic basic, it's not just the Ka or the Kb values. But you can kind of see how those things are related with these two weak acids and bases here. And I would encourage you to try and do like the pKb and do like this similar sort of calculation and see what you get. And it's kind of interesting. So when we're talking about a strong acid, it's going to dissolve completely. That's typically what we say in like a high school class. We'll say this is like 100% dissolved. In reality, there is still a little bit of this stuff, but it's such a small number that we can assume it to be 0. And this is so much more stable. It pretty much all of the ions are going to be this. It's still technically a base. It still can technically accept protons, but you're just going to need an insane amount of this to get any of that for the K equilibrium. So if you have like HCl and you had 1 molar, like the standard concentration, you can actually like think about this being so close to 0 that it's effectively 0. Like it's going to dissolve 1 molar, like all the stuff is going to dissolve, and it might be like a couple molecules not dissolved, but not much more than that. And so with the relative scale, there's like billions of these things compared to like just like 1 or 2 of those. And so we can think of the K in this sense as kind of like approaching infinity, or it's getting bigger. And so these K values typically are not given for strong acids and bases, especially at like a high school level. They might do it like college level because you can do K equilibrium with strong acids and bases. It's just you get really weird values when you look up these concentrations, because you can think about this as basically being our HCl. Those are the red dots right here. I've tried to color coordinate it, and this will completely dissolve. With the number of molecules I've drawn here, it would be inaccurate to even turn one of these red, because it's not like one of these for every 1, 2, 3, 4, 5 of the purples. It's more like one for every like 200 million or something of these guys. So it's so much in this favor of the product that you can say there's basically no reactant left. And it's also important to note that most Ka values for most weak acids, these tend to have like a negative in the exponent to show that they're kind of a small K value. But when you start talking about strong acids, oftentimes these end up being positive exponents to show that it's a very big K value. That's really favoring the, you can think of this as like a lot of products to very little reactants, right? So it's going to be producing a whole lot of product. You're going to have a larger K value. And then you can also think about this in a sense right here as like, this is the concentration of HCl, which is small, which ends up making the whole Ka value small. And then if you make it, the Ka value be so, the Ka value be so large, it ends up making the pKa value be negative, because this is a negative log. It's like saying it's up to that positive power, right? You can kind of see how there's this 6 right there, and this is kind of like 1 times 10 up to the 6.11 power. And then if you negative log that, you would get this value. And then you can see its pKb values. It's very strange with this thing, but basically what we're saying is there's very little of the HCl. And so there's a small amount of HCl, which ends up making there be kind of a small Kb value, like an incredibly small Kb value, because this is a terrible, terrible base, which ends up making a large pKb value. Because strong acids, their conjugates are terrible bases. That's why this number is so small. Whereas its a Ka value was fairly large. And you can think about this as like very large number times very small number. If you multiply the Ka and Kb, you should get 1 times 10 up to the negative 14. And if you look at the exponents, we've got 6 and negative 21. Just doing your exponent rules to estimate, you can kind of see that that relationship. And then this is the basic reaction that I used right here to get the Kb that I wrote out there. Okay, bases are pretty much the exact same, just you're flipping how you're looking at things. So very similar to the strong acid, the strong bases, they're going to dissolve completely. They're going to dissociate completely and turn into their conjugates. So if you have like Na, OH, and it dissolves, you can then consider the sodium and the hydroxide ions to be the products. So this is a stable ion. Yes, it's technically an acid, but it's very bad at being an acid. It still can accept hydroxide ions. You can think of that as like donating proton ions. It's kind of like the same thing. Like you can consider the opposite reaction where you've got the sodium right here, and that's reacting with water. And then this, you'll get the sodium hydroxide and some acid being produced. Now, this is terrible at doing that, though it still technically can do that. It's just not really going to unless you had a very, 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 very large amount of these. Then you might get some of those, but on a scale, it's so small. This number is so small compared to that number that we can effectively say it's 0. So if we're considering this, we're saying that this base, it dissociates completely all to the sodium and the hydroxide ions. So all of it will dissolve with our ice table here. We had 1 molar, we changed, got rid of that molar. Now we've got effectively 0 left of this, and we've made it all be the products. So we can see here that I've drawn out all reactants, and then they dissolve completely, and we have no reactants left. It's all products. And we can look at the math for these things. And this is for the sodium hydroxide. We've got the Kb value and the Ka value here worked out, as well as their pKa values. And you can see that similar to the acid, that when you have this base and you think about its Kb, it's kind of weird, but the Kb is going to end up being positive, right? So you've got such a small amount of this number that ends up making the Kb be a large value. Or I should say it ends up making the exponent be positive. So this is a large Kb value, and then that ends up making the pKb decrease in size, so it's becoming more negative, and it eventually becomes so low that it turns into these negative numbers with the pKb. And that's indicating that now we're starting to have positive exponents for our Kb. So this is a very small number here, which causes this to be large, which will then kind of shrink down the pKb and make it become more negative eventually. And then with the Ka, we've got this similar sort of deal where this is very small of the sodium hydroxide. This is much more stable. And so we have small number here, which makes a small pKa value, which then ends up making a large pKa value. Because remember, these are like those exponents. So also keep in mind that these different numbers, these came from slightly different sources. So I've been working with this number and that number, but it's really hard to get a Ka value for some of these strong acids and bases. They're variable, and I can imagine that we're dealing with such small concentrations of sodium hydroxide that there's some experimental error that comes in when we're trying to measure those concentrations. And same with like the HCl. Like, yeah, sure, there might be still a couple of them floating around, but there's so few, it's kind of hard to measure them. And so they've got these inconsistent Ka values and pKa values when we're talking about the strong acids and strong bases. So just be careful with those. Probably if you're seeing pKa and pKb, especially if you're in like high school and AP chemistry, you're working with a weak acid or weak base that also has a conjugate of a weak acid and a weak base. It's very rare for people to really consider these guys like weak acids and weak bases. Like most people would not consider that to be a weak base because it's so stable. It doesn't turn very much into the HCl. So it's kind of hard to consider that a base. So it really depends on, are you defining a base as something that can accept any amounts of protons, or does it have to be a significant amount of protons? And if it does have to be a significant amount of protons, then I would not classify these as bases, but I would just call them these stable ions. So when I think of these things, I think of strong acids and bases being paired with stable ions, and weak bases and weak acids being paired with each other. I don't even call these things weak acids and bases in my head, though technically, by definition, they still could be considered a very, very extremely weak base or extremely weak acid. All right, that's it. Thank you for joining me. This has been Andrew McLaren. Thank you for McLearning with me. I've got a few more offers that I'd like to let you know about, and remember, like and subscribe. For each video on YouTube, I am making an interactive version using HP5. These will be for sale on Podia, and if you click on the link in the video, you should be able to go directly to that product. I also have 2 demos I'm going to be linking so you can kind of see what these products look like. So I would recommend checking out those demos. I also offer one-on-one remote tutoring through Wyzant. Please use the links that I have linked below. That way I can get 100% of the hourly rate as opposed to 75. Each video also has a link for my Patreon, and you can join at the $3 level to get some resources I use for tutoring or to support the channel. And I also have a $5 raffle level, which you could either get some free online tutoring or 5 interactive lessons for free. You choose which ones. And then I also have my Teachers Pay Teachers, which has some old lessons that I made from when I used to be a teacher. I may be adding to that. Thank you for spending your time with me. I hope that you learned something.